Hi there. Excuse me. Nothing like starting out with hacking. So let's take a look at problem 16. And it looks like you have things pretty well in order. The big problem that I saw um, when I looked at problem or part C, um, what we do is say, look at the expected values in the first row. So if you were to calculate those, you would have 10 times 4 divided by 45, and that's going to give you your 0.889. Um, Usually when you have expected values that are less than 5, sorry about that, um, our results are kind of suspect. We really want to have large values for those, so I would be concerned with those particular values. Okay, all right. So that's the only thing I saw in 16. In 17, so here's our table. So you've got 28 and 6, you've got 251, 273, and you want to construct your odds ratio. So what you're going to do is take the 28 divided by 251, that whole thing divided by 6 over 273, and when you do it all out, it comes out to be 5.091. That's okay. Don't be worried that it's greater than 1. Okay? So you need to calculate the confidence interval, and you need, of course, a standard error. So you're just going to take the 1 over the ratios of the values and take the square root of those. So when you do all this stuff out, so you have 1 over 28 plus 1 over 251 plus 1 over 6 plus 1 over 273. Those are the values in the middle of the table. Add those together and then take the square root, and you will end up with 0.458. Okay? So then to generate the confidence interval, you'll take E and raise it to the log, that's the natural log of the odds ratio, minus 1.96 times the standard error. And then the upper end will be E raising that to the log odds ratio plus 1.96 times standard error. So then I plugged in some values so you could see how it is generated. And you end up with a confidence interval that runs from 2.074 through 12.492. Okay, so that was pretty exciting. So it looks like you had 20 part A pretty well. And what we're going to do is take a look at the other tables. So what I did is calculate the odds ratio for each table. Do I think it's appropriate to combine? No, actually I don't. The reason being, if you look at the values, even though our sample size is pretty close, it's not that terribly different. Look at how much larger our values are for CAD and yes and CAD and no. Or excuse me, CAD and yes is the big one that I found a little bit concerning. So I don't think it's appropriate to combine the tables. But we did run the Mantel-Hansel test, which I can still never pronounce. Here's the pooled value, and the R output is a little bit below. I'll talk about it in a minute. So there is the pooled value. Here is the 95% confidence ratio, excuse me, confidence interval for that ratio. And we would reject the null and say that, association, we would reject the null and claim that, sorry about this, claim that association does indeed exist. Okay, so then I put in the R output, and let me show you how it's generated, because that's no fun. What I did is actually just take the little tables and put them into a matrix, and the same one for the second table. And you need a package called lawstat. So I don't know if you have that or not. I just downloaded that. Okay, so you install library lawstat. Then you create a three-dimensional array. You use your matrix 1, matrix 2. So you're going to have each of the matrices is 2 by 2, and there are 2 matrices. So 2 is the number of matrix. The first one is the number of matrices, which happens to be 2. Then each matrix is of the order 2 by 2. Okay? Then here is your Mantel-Hansel test. You've got your test statistic with degrees of freedom. And the p-value is your 2.1, oh, my fault, 0.000218. There is your pooled odds ratio, and that's what I was getting at when I did the confidence interval. And this is just the combined. If you wanted to see what the combined matrix is, all you do is add them together. So that's what they look like. Okay? All right, I hope this helps. If you have any more questions, let me know. All right? Thanks.